Hey, hello everyone. Today I'm going to go over some basic calculus, which you guys are definitely going to need in some higher problems of physics. By the way, in this video, I'm just going to go over the calculus you guys are going to need for solving simple physics problems. I'm not going to go over the advanced level of calculus. So it's just some introductory calculus for some questions of instantaneous acceleration, velocity, and maybe simple harmonic motion. I don't know. So today we're going to go over. This video has been divided into two parts. This is the first part, which contains differential calculus. Differential calculus. That is off-centered. I think that should be fine. Yep. Okay. Differential calculus. There we go. So, why do we use calculus? In what scenarios do we use calculus? Well, we use calculus when we have to take. Okay, well, let me demonstrate this with an example. So, suppose there's a point here, A, and there's another point here, B. Now the distance between A and B is, say, 20 meters. You start up your car here and you drive from A to B and take a good 10 seconds. And I tell you to calculate the average velocity during this journey. So if you have watched my videos, or if you know how to calculate the average velocity, you're going to say that the average velocity is equal to total distance upon total time, which is 2 meters per second in this case. But this does not necessarily mean that at any point in the journey your speed is going to be 2 meters per second. Chances are, and there is a really high chance of this in the real world, that your velocity may say is 5 here, it is 1 here, and then if you take out the average of all these velocities, you get 2. But 2 meters per second does not give you the information about velocity at an exact point. So, calculus enables us to take out the instantaneous calculations of our quantities. Now, the problem with instantaneous quantities, let me tell you. So, why can't we calculate the instantaneous velocity, acceleration, everything with the normal calculation, normal arithmetic that we do? Well, it's because when we are taking the velocity, we're always talking about 2 points, because there is a distance between them and there is time taken to reach the distance. But right now we're talking about a singular point, the velocity at this point. That does not make sense to an intuitive person. Because there are no 2 points here, there is no distance. And also there is no information about the time. So we need to take out the velocity at this point, which is a bit tricky, as we only have 1 point. And our basic arithmetic does not allow us to take the velocity at one singular point. Now, what calculus attempts to do is, we take 1 point, we need the velocity at this point. What we do is we take another point extremely close to this point. This is a really big over-exaggeration of the point I'm trying to make. This point here is infinitely close to this point here. The distance between these 2 points is comparable to 0. The distance is almost 0. This distance here is too big. It was just for demonstration purposes. So that's what we do. We take a point, we take another point extremely close to that point, and now we can take out the velocity. So let us learn how we can do that. So if we now do some math, can you guys see the graph? Now you can. Okay. Suppose I make a graph of y is equal to x squared. Very simple graph, very simple function. X squared goes somewhat like this, makes a parabola. That is not how a parabola looks. It's symmetric about the y-axis, something like this. Has a focus about here. Of no concern right now. Okay. Oh my god. Okay. So here's the parabola. Why have I drawn this graph? Well, to prove a point. Now suppose I want you to to tell me the slope of this graph at this point. Now a person who doesn't know calculus is gonna be like, oh my god, the slope is this here, the slope is this here, the slope is this here, the slope is constantly changing. Then how am I supposed to tell you the slope which is here? There is no way, but there is a way using calculus. So, okay. Y is equal to x squared. Okay, so I tell you to tell me the slope at this point. Let me draw the tangent at this point. Now tangent at that point, the slope of the tangent at that point gives me the slope of this point in the graph. Now, how can I draw a tangent to this point? A tangent is a straight line in this case. A straight line needs exactly 2 points to make. Oh that is incorrect. Okay, so a straight line needs exactly 2 points to be completed. Without these 2 points, you cannot make a straight line. If I give you 1 point, sure, you can make a straight line like this, but you can also make one like this, like this, like this. There are infinite number of straight lines you can make with 1 point. So a unique straight line is defined by 2 points. The problem here is that I have only given you 1 point, and you need to make a straight line using 2 points. What you're gonna do is take a point which is extremely close to this point. Just as we talked earlier, this point is extremely close to this point. The distance between them is almost 0, and then you can make a line like this, and to a very good approximation, it is going to be the exact line you're searching for. And the slope of this line will give you the slope of this graph at that point. So, let's try to do this. Let's try to see how this works. Let's replace y with f of x is equal to x squared. Let's call x squared f of x as a function of x. Now let's see. Now we know the slope, represented by m, is the change in y upon the change in x. So this should be, change in y is just f of x, so f of x2 minus f of x1. So x2 and x1 are different values of the function at different x's, divided by x2 minus x1. You guys can see it now. Okay. So we won this. We won this. But a problem is that this second point is extremely close to our first point. So let's see how we can go around that. Let me write this so we have some space here. Let me write our function f of x is equal to x squared over here, just for reference. We need a very small change in x. Let's call that change in x delta x, because delta usually denotes change. So I go in my, this is the miniature of my graph. It's my graph. I go from this point to a very small point, this here. If I make this bigger and I show you closely, so there is in the x-axis, this is my x, and this distance should be x plus delta x. This point is x, this point is x plus delta x. Why? Because I travel this delta x, a very small distance from this point to this point. Delta x is extremely small. It's almost equal to 0. And the y here should be f of x, and the y here should be f of x plus delta x, like that. The slope that we want, let me write that. The slope that we are looking for is f of x plus delta x minus f of x upon x plus delta x minus x. Yep, that's the exact formula I wrote before. It is just y2 minus y1 upon x2. This is y2, not y squared. x2 minus x1. It is our second y minus the first y. The second x minus the first x. That is what we want. These x's cancel out. So what we are left with is just this. Delta x. Now, what we want is this delta x to be extremely small. So small that it should almost be 0. So what we write here is something fancy, a new function which is called the limit. Denoted by LIM. Limit is a limiting case of a function. So I want delta x to be as close to 0 as possible, but not 0. As close to 0 as possible, but never exactly 0. That is what this thing means. Delta x, this does not mean that delta x is equal to 0. No. It's just extremely close to 0. It's never exactly 0. Sorry for the background noise. There are kids playing outside my home. Okay. So, that is what this function means. Limit. Let's see how we can go about this. We know that f of x is equal to x squared. So f of x plus delta x would just be x plus delta x whole squared minus f of x is just x squared, as we talked about here, divided by delta x. Nothing fancy as of now. Let's evaluate this term. As we know, x squared plus 2x delta x plus delta x whole squared minus x squared upon, that upon is disastrous, upon delta x. Nothing fancy. Cancel out these x squares. We get 2x delta x plus delta x squared upon delta x. Let me erase this on top here. Let's remember that this is the limit as delta x approaches to 0. This is how we call it. Delta x approaches 0 because it's approaching the value but never becoming exactly that value. So this is what we got. Coming back on top, I can factor out delta x from this numerator. So let me factor out delta x. What remains is 2x plus delta x upon delta x. Now I can cancel out these delta x's. Now some of you, I don't know, but some of you may point out that delta x is close to 0. How can I cancel them out since I cannot cancel out 0 like this? But delta x is not 0. Delta x is just extremely close to 0. Even if I do something like this and then cancel them out, that is perfectly fine. That is not perfectly fine. There should be another 0 here. But yeah, now that is perfectly fine. So this is as small as maybe, yeah, that's a lot smaller than that, but never 0. So we can cancel out delta x like that. And what we are left with is 2x plus delta x limit of delta x approaches to 0. Now delta x is extremely small, so we can ignore delta x here. It's not 0, but it is extremely small to be neglected. We can neglect delta x because it is extremely small. That doesn't make a difference in our calculations. So if we neglect delta x here, we get 2x. What does this mean? We were searching for the slope. This means that the slope of that graph at that point is equal to 2x. Suppose this point is 3, 4. Then this slope here, the slope of this graph here at this point should be 2 times x, which is 2 times 3 is equal to 6. That should be the slope here. Yeah, pretty interesting stuff there. This is calculus. If I'm doing something like this, I'm telling the delta x is extremely small in a function like this, which I just did. This can also be written as d of f of x upon dx, where d of f of x means a very small difference in f of x. This is exactly similar to delta fx upon delta x. You guys are familiar with delta. Delta means change, but d means a very small, infinitesimal change. A change so small that it's almost 0. So this can be written as d of f of x upon dx. So what we just concluded is that d of x squared upon dx, so change the function of x squared upon changing the function of x, an extremely small change, that is equal to 2x. That is what we just proved. Now I'm going to go over some general formulae for these differential equations, because you're not going to derive these every time. Maybe in the next video I'll maybe give the derivation of some of these formulae, but I'm just going to give you some very important formulae that you're going to need in physics. So the first and foremost, the most important formula of all time, most important, is that d of x to the power of n upon dx is equal to n into x to the power of n minus 1. This is the formula you're going to use most of the time, and we can verify d of x squared upon dx. So this thing comes before x, and when it's subtracted from this thing, the 2 comes before x, and 1 is subtracted from 2, so that is power of 1, which is 2x. Just like that, dx cubed upon dx, 3 comes before x, so 3x, and 1 is subtracted from 3, so 3x and 3 minus 1, 2, 3x squared. d of x cubed by d of x is 3x squared. The most important formula you're gonna need. Also, dx by dx is 1, because these just cancel out. Also, you can show it like that, the x has a power of 1, it comes before, and then the power is canceling out, so only 1 remains. There are multiple ways to show this. Differential of a constant, so like kb constant is 0, because a constant means that there is some number and then x to the power of 0 is there, because x to the power of 0 is just 1 dx, so the 0 comes before and it makes everything 0. we can always take out constants out of differential equations, differential expression equations. So d of 3x squared can also be d of 3x squared upon dx can also be written as 3 times dx squared by dx, which is just 3 into 2x, which is 6x. And you can calculate it this way. So 6 and then x, 6x. So this is the most important formula, and 2 or 3 more formulas. So d of sine of x upon d of x is cos x, and d of cos x upon d of x is minus sine of x. Maybe I'll try this in a future video, but it is but just right now, and this video is already too long. I think this is the longest video on my channel right now. So yeah, good luck and bye.